So here I start off kind of nice. What's this guy here? Yeah, this should be 5x to the 4th. Negative 33x to the 10th. Cool. Nice and easy. This one's not too bad, even though it's got more stuff in there. Yeah, see, that totally is lost, right? That is related to the fact that if I give you a slope, you have no idea where the function goes. Because if it was a derivative, it lost information about its y-intercept. For example, for one situation, right? I like it, I like it. This guy, negative 15x to the negative 4, beautiful. Yeah, this will be 2/3 x to the negative 1/3, I like it. Now this one you rewrite as, yeah, right? Remember that roots on the bottom like plants? Powers on the top because they're powerful. And then, so the derivative would be 9/7 x to the 2/7. Now real quick, look at this one. I don't know if you guys remember, but earlier I put an example. In this case, this would look really strange. If you tried to graph x to the 2/3 in your calculator, are you alive? Let's see what it looks like. Hey, you're alive. Yeah. All right. I'm just going to do it over here real quick. All right. Go ahead. Stop. X to the 2/3. Boink. This is one of those. This is one of those in the wild. This is one of those that have that cusp thing that you're like, I've never seen that before. Well, there it is. Yeah. So what should be true about the derivative at 0 then? If it's got that cusp going on. There shouldn't be a derivative at 0. So what happens, sure enough, what happens when you try to plug 0 into the derivative? This is 2/3 over x to the 1/3. You get undefined. It's x to the negative 1/3, right? So the x is on the bottom, so you get it undefined. There you go. It matches with the picture. That cusp thing that we were talking about before. I like it. Okay. So let's look at this one, the one that I was told looks gross. What happens? You first have to do what? Cool. And actually, if I rewrite this for myself, this is going to be negative 2x to the negative 1. So f prime is going to be 12x to the 3rd plus 2x to the negative 2. So if I look at the point 2, I get a slope of 2 cubed is 8 times 12 is 96 plus 2 over 4, 96.5, right? So if you do that, yeah, you get 193 over 2. Nothing wrong with that. That's beautiful. And then, is that right? So then you get y minus 47 equals m times x minus 2. So your y equals 193 over 2x. Multiply these, you just get minus 193 plus 47 is 146, I think. Is that true? Minus 146. Is that cool? You bring the 993 over 2 in, the 2's cancel for the second part, that's awesome. Yes, yes, yes? Okay. not too bad. And then this guy, what is f prime?
2x. 3x squared.
And I want to set this equal to 0, right? I would, before I do anything, I would, huh? Yeah, I'm going to divide by 3. Shit, yeah. Make all my stuff smaller, then I can factor this thing. Yeah, plus 7 minus 3. So we get x equals -7 or 3. Those are the two places where it's a horizontal tangent line. So they could be max and min. I like x. That's awesome. Could you imagine doing limit definition for this whole thing? No, I don't want to anymore. Yeah. So we proved 4x to the n, then we have the definition, the derivative laws, the derivative rules that allows me to just do each piece separately for addition subtraction. That's awesome. Those together make those easy. Polynomial derivatives, easy. Let me ask you this right now, since we just talked about this stuff. If I had, if I told you, let me do it up here. I'm not really used to the projector's business. Camera, you're drunk. Okay. I told you that g prime of x equals, what you got, Jim? 8x cubed minus 3x to the 3x squared. What's g of x? You see how this is backwards? But yeah, good. Cubed would have come from a fourth. A 4 would have come down. There must have been a 2 there. I love it. That's kind of how you can piece that together, right? What about over here? There you go, buddy. Just gotta know your limits, Cameron. Alright, so I like to ask that kind of question. Now notice there's something kind of wrong here. There's one thing a little wrong. There could have been a number that we lost. I love it, so a lot of you guys know this already, but later you're gonna hate when I'm writing all over your paper. Plus C, where the hell is C? Anyway, so what we just did right there is an antiderivative. Right? That's in our future, but right now it's easy as shit to kind of think about it in this case. Right? This is such a nice derivative rule, I can undo it really easily. Now, I want to look back at, there's something else in that paper that looks at sine. And I use the limit definition to look at what the derivative would be. And what's really kind of cool is, so you guys remember this, there's a trig identity for the sum of the angles inside of a sine. Sine is the nice guy, cosine is the asshole. Sine says, hey cosine, let's take turns. And there's a plus there, I'm going to leave it as a plus. I don't want to, cosine would be, if this was cosine, it'd be cosine and cosine, me first. And you got a plus, screw you, and put a minus. What do I mean by that? I mean, what's cosine of A plus B? That's cosine A, cosine B. See, freaking asshole. He's like, I'm first, screw you, sine. And sine's like, okay. And then the little please says, you got a plus, I don't give a shit. And then now it's your turn, sine. All right. And you're all like, dude, calm it down with the math. Shit, these aren't really living things. I don't care. Else me wrong. Sine is a nice guy. So he's going to say, let's take turns as cosine. There's a plus sign, it's going to stay a plus sign. By the way, just in case anybody knows about these things, you guys realize that's not, if you know about this, if you don't worry about it. This isn't hyperbolic cosine. If you have no idea what I just said, we will talk about hyperbolic trig functions later. And you're all like, sounds painful, but we'll get there. Now, if I let h go to 0 for parts of this thing, right? Because I can break up the limit between all three of these. What happens to cosine as h goes to 0? What happens to cosine as h goes to 0? It goes to 1, right? Because cosine of 0 is 1. So this is sine x over h plus, what happens to sine as h goes to 0? Yeah, this part will be 0, right? And then, so if you want to follow, where's it at? Here. Oh, and this is where we got to be a little careful. Yeah, all right. So I am kind of waving my hands a little bit here, but so I can split it up like that. These two, of course, cancel. And I think we talked about earlier this semester. Didn't we talk about this? Yeah, we did talk about this, right? Yes? So this sine h over h actually goes to 1. Remember that was 1? So this is showing you that the derivative of sine is cosine. And if you look at the graph of sine, why does that make sense? Make a little quick sketch of sine x. Make a little quick sketch, quick. You don't have to have any scale or anything. Or stare at me. What's your favorite wall? I'd rather you do it, though. Okay, all right. You're all like, we know you're going to do it. Just do it for us. Good Lord. Try and do some shit. If I start looking at this like we were looking at it earlier, how would I graph the derivative of this? I'd find where, yeah, so that's a place where it equals 0. There's a place where it equals 0, right? I like it. And it's positive in between here, right? And then it's negative in between there. Well, what's that look like? Cosine. I love it. Now, this is not a proof. That's more of a proof. What's interesting is right here, the slope through there is 1. So that is 1 there. So visually, it makes sense that this is going to happen. The derivative of sine is cosine. Now, what about the derivative of cosine? Real quick. Let me see if I can push this a little bit. What's cosine look like? Where does he start? Well, it looks like the black one, right? So if I start this off, yeah, and it just goes on, right? Like a little octopus. I always think this is an octopus. Would be nice. So here's where he's 0, here, 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 for example. But look at the problem. Back here it's positive, right? And over here it's negative. Is that sine? No, that is negative sine. So if f is sine, the derivative is cosine. But if I got cosine, the derivative is negative sine. Not factorial in case you know. I always get some smart ass. Factorial? No. That's kind of nifty. You could actually do this the same way we did that using this guy. Right. Okay, so that's the other thing I had up there. I want to talk about that real quick. This is perfect. Oh, I kind of hate that they put this here, but I'm going to kind of expand on what they've done. I'm I'm going to give you a problem to look at, and you're going to think it's unrelated, and I don't care. Look at this. Make a table of values to investigate those limits. Because how else would you do it? Can you do something mathematically to analyze these limits? Doubt it. So, make a little table. Now, this is good. This is a little review because you're going to have to be able to do this for the test anyway. You're trying to get towards 0, right? So think about what values you want to let h kind of step in a little bit. I'm just going to let you guys try something. All right, so what are you guys using for h? $30? What are you guys using for h? How are you guys making this table? Which is something you're going to have to be able to do yourself when the test comes. Okay, I like it. So you could start like, you could put -1 and 1. That's pretty far away, but you know. And then it can go to, okay, I like it. And then, so let's start off with like -0.5 and 0.5. Or I will anyway. You guys could all have done something similar. And then you go to 0.1 and -0.1 and 0.1. And maybe 0.01, negative and positive, right? So stepping towards 0 from both directions. That's that idea of limit from before. So when you plug a -0.5 in there, this is my table, so I'll do this. No joke. I get 0.586 roughly. I put -0.1 in there, 0.67, -0.01 in there, 0.69, 1 roughly. If I put positive 0.01 in there, 0.696. I'm just going to do one more, 0.1, 0.72 roughly. So right here is what I'm looking at, right? That's coming towards 0 from both directions. So if I had to hazard a guess, I'd say it'd be right in between these two, right? Maybe like 0.6935 roughly is my guess. You guys with me so far? Okay, stay with me, stay with me. This looks roughly like stuff we've done. I'm not going to tell you what it's used for yet. If I did this one, I could do the exact same values again, right? Same exact values. Oh. here I get, whoa, shit. Okay, yeah. 0.846 or 0.845. I'm using the same values. Is that cool? Just don't want to rewrite them. Rewrite them, Jeff? You want to rewrite them? 1.04. Oh shit. Okay. Yeah, that works. 1.09. That's the bar right there. And then if we put 0.01 just to cut to the chase here. 1.105 it looks like. So right in between those two would be 1 point, I don't know, 0.15. Yeah, something like that. No, Jeff. Oh. Is that right? 75. 75. Oh, good. You're smart. There you go. Yeah. So that's my guess. The same way I guessed there. That's my guess for that. Now watch. If you have a calculator, what's the natural log of 2?
It's like 693.
0.693. Oh shit! What's the natural log of 3? 1.099. Like 10986, blah, blah, blah. Roughly. So it seems like the limit as h goes to 0 of a to the h minus 1 over a is the natural log of a for a's that are in the domain of natural log. Are you guys with me? Have I proven that? No. Am I going to prove that? No. But, watch this. If that's true, let's investigate. If I have a function 2 to the x, what is its derivative? I don't know, so what do I have to do? If I don't know derivative, I got to use what? What do I have to use if I don't know derivative? I've got to use the limit definition. Our favoriteest thing in the world. All right. Guys, everybody's with me. This is going to be... a lot of you guys are like, I wish I could be, Jeff. So I don't know this guy's derivative. Is this the right form? Now let me just nip some of you guys in the bud. Is this the right form to use power rule on? Oh, hell no. Don't be bringing that x down and making an x minus 1. What's the form for power rule? Variable to number, right? Is that what that says? No. These are very different functions. Why in the world would their rule be the same? It's not. I like it. So we're trying to figure out what the rule is. And how we figure out what the rules are, we have to go back to the limit definition. So what would this look like? Limit h goes to 0. What would be inside here?
2x to the minus
2 to the
x plus e
x plus h minus
2
to the x all over
h.
h. Now, let's see if you guys can do this. This is going to happen so often in calculus. You're in calculus, but also any other calculus you might have to take. You've got to be totally used to what I'm about to do. Can I break that up?
2x
Say again, sorry.
2 to the power x into 2 to the power h.
And what's the operation in the middle?
That is exponential
2 to the x
into 2 to the power h.
times 2 to the h. I love it. Because, of course, when do I add powers? When I was multiplying the like bases. So you can just pull those apart. People are always like, in my Calc 3 class, they were still like fascinated. How did you do that? Like, oh my God, no. This is normal shit. It's going to happen a lot. All over h. Now watch. What part of that doesn't give a shit about h?
2 to the
2 to the x. So I'm going to take it out. It doesn't care what h is. It can come out. And what's left? 2 to the h minus 1 over h, which we didn't prove, but still, it actually is true. This is 2 to the x natural log of 2. If I did 3 to the x, blah, 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 bam, 3 to the x natural log of 3. So I bet you a to the x's rule is a to the x times natural log of a. Oh shit, that's exactly what it is. Later this semester we'll see another way to get that result. If I have a to the x, the derivative of that is a to the x natural log of a. And if you look at it, what's an exponential look like? Exponential function, what's it look like? Can you guys do it in the air? Yeah. Shwa. Right, so it's shwa. If I do what we were doing earlier today, is there a place where the slope is 0? But the slope is approaching 0 back here, isn't it? So it seems like it starts off small positive, and then what's the slope do? Gets more and more positive. So this is the one place where it follows it almost perfectly. There is one function who is its own derivative. Natural log of what would be 1? Natural log of what is 1? E, because the base on natural log is e. So if I have e to the x, the derivative by the rule would be e to the x natural log of e, but what's natural log of e? Freaking 1. E is such a kick-ass cool number. Oh my god. Which is why we gave it the simple e. Euler gave it that symbol, but not named after his own name. It was just like the next variable he was going to use for some interesting numbers he was looking at. He's like, well, I always use B, C, D. Oh, just use E. And, you know, yeah.
So the rule in the top right that you just showed us, that only works when x is just x, right? Like if it's not like x plus 2 and then x plus
Yeah, for right now we'll say it only works if this is, now to be honest, if there's a whole idea about taking derivatives when you have a function inside of another function. If that inside function is linear with a slope of 1, it doesn't change anything. So what you just said, it would actually, x plus 2 would still be x plus 2.
But like if it was like x
3x minus 7 or x squared minus natural log, oh shit, then that's got a lot of other crap to worry about, yeah. Yeah, so get ahead of us. That kicks ass. That kicks so much ass. Right? That's awesome. Give me a lot of those to do, because then the answer is sitting there staring me in the face. Oh, cool. All right. Let me see. Yeah? What time is it? Yeah. Okay, cool. Let's do one more thing, and then we'll head out. So now that we actually have a decent amount of derivatives that we don't have to use limit definition for. Including some trig stuff too. I want to start developing ideas of how to build derivatives of other functions. So I want to be able to take derivatives of functions that I know, combine them somehow to get derivatives of other functions that I don't know yet. So I need to start developing rules for derivatives by themselves. Just how would it work if I had a function times another function? What would that derivative look like? You guys get what I'm saying? So if I had, I know how to take the derivative of e to the x, and I know how to take the derivative of x squared. How would I take the derivative of x squared times e to the x? That's what I'm saying. Both of those derivatives are easy. You'd hope to God that the derivative of this would be sort of easy still, even though it's a combination of the two, right? Product rule. Kind of makes sense. So when you have a product of functions, I want a rule for what to do. Thank God there is a single thing that you always do when you have a product of two functions. You have to know what each guy's derivative is. But if I know that, I can get them. Let me see. There is let's just do this part, and then I'll see if I can remember the other part. So if I have a function that is the product of two other functions, and I want to know what h prime of x is. I don't know what it is, so I use quadratic rule, because we haven't proven that shit. I don't know what it is, so I have to use limit definition. So like, if you wanted to graph something, but you don't know what it looks like, you're going to have to use a table of values, right? That's the base thing to do, right? I don't know what that is, so I better use the base thing, which is limit definition of through. So h prime of x would equal the limit as h goes to 0 of this. Is that cool? That's just straight up limit definition. Now, there's a certain thing that happens very often in mathematics. The one place you guys have done this already is when you complete the square. Do you guys remember completing the square? So like if I had, real quick, side note. So if I've got f of x equals x squared plus 6x plus 2, how would I complete the square to put it in like standard parabola form so I can see the vertex, all that kind of shit? How would I complete this guy square? Who remembers? What are the 2 steps? Yeah. So I can make some room.
I think it was dividing the 6.
Yeah, you cut the middle term in half and then square it.
Square.
Let's think about it. If I square x plus 4, don't I get x squared plus twice 4 plus 4 squared? So whatever the middle one is must have been twice what this was. And once I know what that thing is, I square it to figure out what should have been there. That's why the 2 steps work. So if I cut the middle term in half, I get 3. So that's how this is going to factor. And then if I square this, I get 9. So look what I have to do. Don't I have to add 9 and subtract 9, right? To keep the balance. I like it. Now watch. So what I'm going to do now, oh shit, now I got to make sure I remember which way this goes. I'm going to do something sort of like that. I added something and subtracted the same thing, which overall I didn't do shit, but I reorganized it so I could actually factor part of it, right? And of course this would be -7, the vertex would be -3, -7, bullshit, right? The rest of it. Not bullshit, but the rest of it. So now what I'm going to do something very similar to that. Let me see if I can remember what that is. It's been a while. I'm going to add and subtract something in the middle here. I'm going to add and subtract. Let me see if I can remember. I think it's this. Let's see if this is true. Yes, that's it. Pretty sure that's it. Let's find out if that's true. I love the looks on your faces. And what are we doing? We're investigating rules. We're seeing why they work. You're not going to suddenly have to know when to do this. This is not something obvious, right? Is this okay to do? All day long. Because what did I just do? I added 0. I can do that anytime I want to. You guys, am I with me? I see the looks on your faces. I love it. Let me do the next step, and you can see why somebody might have thought to do this. The next step is, what can come out of these two? G of x plus h, right? And what are you left with? F of x plus h minus f of x over h. Well, what's the limit of this? What's this? Come on. What's this? The limit of this is the definition of f prime. Let's see. Then I've got plus. What comes out of these two? F of x. And the limit is in front of all this shit. Times, what's left when I take an f of x out? G of x plus h minus g of x all over, h. Wow. So was that obvious to do at this step? No. Was it really clever of somebody? Yeah, it's clever, because now look, I can reorganize things into stuff I know. As h goes to 0, what's this? G of x. So what I got? Let me write over here. As h goes to 0, this is g of x. And this is f prime. Plus f of x. G prime.
Do we have to do that? Like,
No,
that?
never.
Oh
No,
my god, damn, like.
no. No. I'm showing you where the rule came from. What are we going to do? We're going to use the rule. It's sort of like proving quadratic formula. Do you have to prove it every time you want to use it? No, of course you don't. You just have to prove it once. Have we proven this rule? Did we do it? Yeah. All right. So why would we do it again? I got it. I could give you an extra credit problem on a test related to this kind of thing, right? I can give you an extra credit problem about any damn thing I want to, because people get extra credit. You guys with me? I'm not going to make you do this and go, or make you do something else and go, can you figure out what you have to add and subtract? This is not obvious, right? It's not obvious until I do the next step, and then you go, oh, but who the shit, came up with that out of their ass? I don't know. I can't remember actually at the moment. So here's the idea. If I have f times g, I love this idea, and I want the derivative of it. They take turns. This is the derivative of f times g, so f got a turn, plus f times the derivative of g. They take turns. That idea is awesome. I can't remember, a while back I had something, I got to remember how I did it. There's a really cool way to show you that it's not just like 2x e to the x. Like you can't just do both derivatives all at once. It's missing something. So I just got to remember how I did that. But this, we just proved the rule. So let's try to use the rule. And something I'm going to say a lot is write the rule and then take derivatives. People try to do it all at once, and then you forget shit, right? So what do I mean by write the rule? I'll show you. Let's do that function up there. Let's do it correctly. They should have this whole proof in the book somewhere, if you want to see it written better. So if I have h of x equals x squared e to the x. H prime of x, so here's my two functions, right? So I take, here's what I mean by write the rule until you're more comfortable. The rule is the first guy gets a derivative and the second guy stays the same. And then the first guy stays the same and the second guy gets a derivative. I wrote the rule, now I'm going to do the derivatives. If you try to do all of that at once, very often something gets forgotten or done wrong. Try to have too much shit in your head. Don't do that to yourself. It's already hard enough on its own. What's this? And of course this is e to the x. That kicks ass. So then I could even, if I wanted to, I could factor this thing out, right? X e to the x, 2 plus x. So where's this guy have horizontal tangent lines? At 0? Makes that 0. And what makes e to the x 0? Nothing. There's an asymptote at 0, right? E to the x can never equal 0. So that just doesn't give you an answer. So it's got a horizontal tangent line at 0 and at -2. Intriguing. Later this semester, we'll use that information to help us sketch a curve, sketch what this thing looks like. Like it. And real quick, let me show you, this isn't quite the right thing, but I did remember this, what I used to do. Remind me, the derivative of x cubed is what? All right, now watch. If I took that and I wrote x cubed as x times x squared, and I thought that the product rule was just take both derivatives and multiply them, right? That's the most common mistake, is people just derive everything, right? And so what would I get? What's the derivative of x? 1. What's the derivative of x squared? 2x. So I would somehow think the derivative of x cubed is 2x. So obviously that's incorrect. If I did this the right way, I know I've written this in a way that I didn't have to, and I don't care. If I do this with that rule, it better agree with what we know is true, right? So how would I do that using the product rule? This guy gets a turn. So what's x? So let me write the rule. X prime times x squared plus x. He stays the same. He gets a turn, right? X prime is 1. And then over here I get x times, what's x squared prime? 2x. So I get x squared plus 2x squared is 3x squared, what it's supposed to be. So this is a nice check. Math has got to be self-consistent. If I make a new rule, it's got to jive with any rule I knew before, or else it can't possibly, one of those things has to go then. Maybe both. Thankfully, I don't have to throw anything out yet. I like it. So here, let me give you, let's see, where things get interesting. Ooh. Oh, yeah, that's gross. All right, let me give you this here. Let's see. And then we'll head out after this one. Got it. Well, that's a chain rule I'm thinking about. That's cool, though. Now the book is going to say, or I think the book does say use product rule on this. Do you guys see how there's another way to do this without using product rule? Obviously you can just distribute the damn thing, right? But if I use product rule, it's got to come out to be the same answer. So if I use product rule, what do I do first? What are my two functions? X and 1/2? And all this stuff. So the rule says you're the first one times this
plus derivative of second.
plus Leave that guy alone. I like it. Yeah. Hopefully I can convince you guys that writing the rule is a great step. Some of you guys will think that you're wasting time, but try to keep everything in your head. I'd much rather go write the rule and then I can just attack the derivatives directly without thinking about the rule anymore. So what's the derivative of x to the 1/2? Times all this business. Plus, leave x to the 1/2 alone. What's the derivative of this stuff?
20x to the 4th.
Good. 20x to the 4th. 5/3 x to the
2/3.
2/3, yeah. 5 minus 3. That's gross. If you wanted to, you'd have to distribute, get your like terms together. My God. It'd be much better to distribute first if it doesn't tell you you have to use product rule, right? I would freaking, sure as all hell, distribute that thing first. Okay, I like it. Yeah, I think, like I said, I think it's a good place to stop. Hopefully you understand that the next thing we'll probably talk about is the quotient rule. What if I have a function divided by another function? How do I take that guy's derivative? Cool. All right. That's enough for today. Monday, of course, we got that quiz to begin with. What did I say? 2-2, 2-3, 2-4. That's what I said last time. I could have put 2-5 on there, but I didn't say that, so I'm going to stick with what I said. 2-2, 2-3, 2-4. On Monday.
Last week, did we have a review sheet for the quiz?
Never. I will give you a practice test for the. Say again?
Didn't you say yesterday you were going to give us a worksheet?
Oh, I said if I thought about it, I was going to make a worksheet, but no, I didn't. I already given you guys enough worksheets, I think. Yeah. We'll have a practice test that I'll give out on Monday for the test that's happening Thursday. Yeah.
Did you pass back Cosine?
Yes.
It's Fernando.
That's mine.